Good morning, everyone, and
morning.
welcome to this Time Goes presentation. I know it's early in the morning, and some of you probably had a few drinks last night. I did, so thank you for showing up. So yeah, this is the Time Goes presentation. My name is Xuan, and I work in the demo team, mostly working on the art side of things.
And I'm Christian Kardach, and I work as a technical animator on the team.
Great. So I'm going to hide behind the computer because I need to play with a couple of things here. So this is the agenda for today's presentation. There are many other things that I guess we could discuss about Time Goes, but we just didn't have time in this presentation. But if you have any questions, feel free to grab me or Chris afterwards, and we would be happy to answer those questions. But the main topics today are creating large environments, high-fidelity visual effects, lighting, and how we build the characters for Time Ghost. We are not playing the cinematic now. Hopefully, you all have seen it yesterday. Otherwise, please go to YouTube and check it out. I think it's like 4.5 minutes or something, and we don't really have the time to play now, but hopefully you know the context of the cinematic. So let's start with environment creation, right? If you've seen the cinematic, and I apologize because some of these thumbnails are actually work in progress, so it's not the very last pixels that you can see in the image in the short film. But if you've seen the cinematic, you probably realize that we have big environments. Generally speaking, it's all about organic environments, like natural environments. We have some handmade structures and some other human elements, but generally speaking, it's all natural environments. So these are some of the challenges when it comes to character environment creation that we face while working on Time Ghost. Large scale, obviously, everything that is large, obviously, represents a challenge in one way or another. There is also the challenge of mixing frequencies, right? Like you have a character that is standing here. Our cameras are always grounded in reality, so everything that we see is from the point of view of the character, meaning that we need details around the character, we need details in the mid-ground, and we need details in the far background, right? And that is always challenging. And a lot of the times, everything is in focus, so having that balance between frequencies is always a little bit challenging. Set dressing as well. These are massive environments. We need to fill them with things. Grass, rocks, cliffs, boulders, mountains, etc. And this represented a huge challenge, and I'm going to be talking about this a little bit later. Ultimately, this demo is not about environments themselves, right? So another challenge was combining those environments with many other elements that some of those are also quite challenging, right? Like character claw simulation, character hair, a lot of visual effects, and many other elements. Realism is also another challenge. And here I'm not talking specifically about photorealism. That is kind of a given, at least in our department, in our team. But also, when I say realism here, I mean building environments that are realistically built. Like we have grass where it's supposed to be, we have mountains where they are supposed to be, the clouds, they appear at certain altitude based on where the environment is placed and all of those things. And finally, another big challenge is performance, right? Because if we combine everything that I just said, it's quite tricky to make it run at least at 30 frames per second rendering at 4K. So when it comes to environment creation, I'm going to start with terrain generation. That's kind of like, where you start this journey. We need some kind of terrain. And when I say terrain, I mean mostly the main horizontal and vertical landmarks. So that will be the ground where the characters are standing or running or dying or performing whatever action they are performing. And the big vertical elements like mountains and boulders and sometimes cliffs as well. So we approach the terrain creation in two different ways. We have environments in the cinematic that are made completely from scratch. And we have environments that are built based on real-world locations. So we have two different approaches there. We relied heavily on height fields, and by that I mean some kind of terrain generator. And we combined that with Unity's terrain tools. In our case, we decided to use Houdini for building terrains from scratch. I guess you can use any terrain generator that you want. The good thing about Houdini is that it's a terrain generator tool, but you can also use any other tools available in Houdini. And another great thing is that it communicates very well with Unity, right? So you can take something from Houdini, take it into Unity, modify whatever you want to modify. If you're happy, you are all set. If you're not happy and you want to do major changes, you can go back to Houdini, using procedural tools, back to Unity. So, iterating is a given and is very flexible. We also use LiDARs. That is for the environments that are not created from scratch, but based on a real-world location. And we also use a lot of drone photogrammetry to create terrains that are close or around the character. I'm going to play a video here, and I'm going to stop it once in a while to talk over it. But basically, this represents the workflow for environments that are made from scratch. I believe we only have 2 environments made from scratch, or 1.5, I should say. But basically, this is the approach that we follow to create those environments. So, this is an overview of the worldscape environment. As you can see, it's very flat. So basically, we started with a blank canvas. We made it from scratch. This is 2 by 2 kilometers, I believe. We planted the main architectural landmarks in there. That guides the process a little bit. Then we sculpted some details. It's quite flat, but with a little bit of terracing. Then we sculpted these trenches. We take it into Unity. And once we are in Unity, this is just terrain tools. We can keep modifying it. We can make big or small, smaller or bigger changes. If we have something really big, we can go back to Houdini and fix it or whatever, right? We do like a very basic texturing pass. We test it through the camera, right? Our cameras are never locked. We change them quite often, but we have an idea. We just test it through the camera. If it works, it works. If it doesn't work, we keep working on it. Like here, we realized that these trenches were not high-res enough. So, no problem. We just keep sculpting them, modifying them, back into Unity, add more details, work on shaders, in this case with the shader graph. We make sure everything looks great from close-ups, from far away, and then we start working on the set tracing. We have libraries of assets. I'm going to talk about this later. But we take one of the libraries that belongs to that environment. We do some kind of set tracing. Again, we iterate, we test through the cameras. Does it look good? Yes. Carry on. If it doesn't, we iterate all over again. Once we're happy with set tracing, the next thing is scattering. We start scattering vegetation, plants, pebbles, other smaller elements. We test it through the camera, and same thing, right? It's always kind of the same workflow in this type of environments, right? So, in a nutshell, that's how we created all the environments that, again, it's only 2 that are made completely from scratch. The other type of environments that we have, they are based on real-world locations, right? So the approach is slightly different, but kind of the same workflow. Like, we're also working with height fields. We're also working with terrain tools. But in this case, we start from something that exists in real world. So usually we start doing virtual scouting. This is in northern Spain, actually. We found a place that we actually liked for the story. We go there, and the first thing that we do scouting, but this time on location. We take the drone, we fly it, We see things that we like. We see how complex the environment is, how many assets we would have to build, etc. This gives us also ideas for placing the camera. But generally speaking, these are just references. We also do a lot of drone scanning, especially around the areas where we want the characters to perform any kind of action. This is going to help us to build the environment later. And then we also rely heavily on aerial LiDARs, right? So here you can see we built a workflow to get everything from Houdini to Unity as efficient as possible. Each of these chunks of the environment, and this is just a small chunk, is 50 million points. So it's very hard to manipulate all this data. Sometimes it comes also with color information that sometimes is useful, sometimes it is not. But it's great to have it. And because it's extremely heavy, if you all... Let me stop here for a second, because I think this is important to mention. If you have experience working with LiDARs, especially with high-resolution LiDARs, like laser professional LiDAR systems, not like iPhone and stuff, you know that it's extremely complex to manipulate that thing, right? Because here, this chunk of the environment is 50 million points. And we have many, many other chunks that we need to combine to create the entire environment. So manipulating points, manipulating geometry is not doable, really. So in our case, what it worked very well was to flatten those point clouds, store the information of altitude for each of the points, and reproject it into voxels, right? So everything you see here, they are boxes, they are volumes, they are much easier to manipulate, much faster. We can clean them up, we can modify them, we can do anything we want. Then we take every single chunk back to Unity, everything in the terrain system, and now we can actually scout in the actual editor. We can place cameras and we can start iterating over this environment, right? Sometimes we are able to export color information from the point clouds, normal maps as well for high frequency detail, height maps that will be part of the terrain system, and sometimes splat maps as well that we can use for layering shaders, textures, scattering, and other tasks. So here you can see our progress in Unity, where we import the high map with the normal map on top to get high frequency detail. Then we create some kind of color map, again, using as a starting point the information in the point cloud, but then we enhance it with our own textures. I will talk more a little bit about that a little bit later. And then we do asset tracing and scattering paths. And once we have that recipe, it's very easy to iterate, so we can do all the shots exactly in the same way. Same thing, height maps, a little bit of set tracing, scattering. Sometimes we actually had to build foregrounds because we don't have that information in the LiDARs, but that's why we have drone scans to rebuild those foregrounds. Again, I apologize. All of these are work in progress. And some of the shots actually didn't make it into the final cut, like the last one over here. But you get the idea, right? Once you have a workflow in place, something that works, it's kind of easy to create more stuff. Right. So to finish with this part of terrain generation, I can say that everything that we build from scratch has pros and cons, and it is the same for something that we build from reality. So some of the pros when we are working from scratch is that you have design freedom, right? You can build whatever you want. That is good and bad at the same time. But something good is interactivity. Again, you're working with volumes, with voxels. It's very easy to manipulate. And it's very easy to work between, in this case, Houdini and Unity. Some of the cons is that it's very hard to make something from scratch that looks realistic. And again, talking about not only photorealism, but something that is built in a realistic way, meaning that you end up with a lot of iterations, right? On the other hand, whatever is built from reality, you have a locked design, you have a goal, you have a target, so it's much easier to get to the final product. You have great references, meaning that you're going to have fewer iterations because you know where you need to end up. And consequently, everything will be more realistic because you're starting from the real world. Some of the cons, though, is that it's actually hard to meet the expectations, right? Because you might think, well, I have all the references in the world. I have a source material that I can start with, but you still need to pull it off, right? Another con is that it's very heavy and it's very hard to manipulate. So unless you come up with some kind of solution, and even if you do, you still need to go through a lot of material in order to process it to be performant in Unity. Right. Let's talk a little bit about asset building. And this was also a big challenge. And the reason why building assets for set dressing was a big challenge is because we had to build absolutely everything from scratch, right? So from a single blade of grass to a rock to a mountain to a cliff, everything was made from scratch. We didn't use any kind of, online resources, libraries, whatever. We built everything from scratch for this project. To do so, we relied heavily on photogrammetry, the usual standard cross-polarization rig for scanning small to mid-size assets. And we also use a lot of drone photogrammetry. We use a little bit of photometric scanning as well, mostly for vegetation atlases and for some of the fabric materials of the character. We use SpeedTree for modeling grass, plants, trees, and vegetation in general. We use also imposters for background assets. We ended up using them only for trees, but we could have used them for anything really. And finally, we also did a little bit of procedural asset creation and, of course, some hand modeling as well. So yeah, here you can see some of us on location, just scanning. And yeah, again, we did cross-polarization for all type of assets, drone scanning and whatnot. And on the top right, you can see a little bit of photometric scanning. We have a professional photometric scanner that we use a little bit, but we also have like a, improvised photometric scanner that we use mostly on location. So we end up with things like this, right? We have way more. I couldn't fit everything in one image. But here on the left side, you have some of the drone scans that we have, which generally speaking is terrains, mountains, and big elements. And on the right side, you can see that we have mid-sized rocks, big rocks, trees, and also we did a lot of PBR materials as well, right? All based on scans. So once we process everything, we take it into Unity, we organize it based on environment. So we have a library per environment, so we can pick and choose. And when an artist is working on an environment, it's cherry picking. Like, let's use these assets here, let's use those assets there. And we have plenty of references, so this is the way to go. Same thing for vegetation. We also built a huge vegetation library. And that's how we did all the set dressing in this demo. Finally, for trees, and again, this is a work in progress shot, but in this shot alone, we have like 1.6 million trees. So for everything that is in the far background, we use imposters. We created the trees with SpeedTree, which, as you know, is a procedural modeling tool. So we can easily create variations, export it to Unity with textures. We enhance those textures with our own materials based on scans, take them into Unity, and we have this one-click solution for creating imposters. So, any SpeedTree tree, we just click on Generate, and it would give us an imposter that is ready to use. Obviously, it only looks good when it's in the far background. You're not supposed to get close to imposters. Actually, with non-organic assets, it works very, very well. But with trees and fine elements, you need to have them in the back. Right. And finally, we also made some procedural tools to art direct this root system, for example. We did all the things, but this one looks cool because we have a photogrammetry asset that looks good, but it doesn't look good enough. So we can improve the look just by creating some kind of procedural tools. And we've done that for many things. And of course, hand modeled assets as well, like structures, buildings, bridges, a little bit of kit passing. So we use all the techniques available for 3D artists, basically. All right. Let's move into scattering, right? Scattering also plays a huge role in the creation of this demo. And as usual, we are combining tools here, right? That's what everyone here does. So we're using Houdini for distribution and rules, and that's pretty much it. What I mean by that is like we have a scattering system in Houdini that is actually just using, standard Houdini tools. We just made some kind of user interface, so we expose parameters for the user. And Houdini basically exports just a point cloud, right? Just points, so obviously very light information. That goes into Unity. And in Unity, we convert all those the points come with attributes, right? So each of those points will say to Unity, well, in this specific point, you need to place this plant or this rock or whatever. Then which variation of that plant? Is it healthy? Is it dying? Is it yellow? Is it green? All that information comes in the point cloud. Then dots will inherit that, place the prefabs in the right place, and convert those prefabs into dot entities, which make them very performant. And it also works with a win system and interaction with the characters. So here you can see a little bit of the process. This environment was quite challenging because we can see grass from the foreground to the horizon line. So there are millions and millions of grass assets here, right? So this is usually what we do. We have a tool in Houdini that analyzes the environment, creates some kind of distribution rules, and basically scatters a point cloud. All these masks are automatically generated based on the rules that we decided for this tool. And everything is done automatically, but you can also do hand painting if you wanted to. Then everything that is available when it comes to vegetation assets, we can feed that information into Houdini. So this is the tool that we have, that circle over there. So there we can basically say, oh, we want to use all these prefabs that belong to this environment. And then we start playing with the settings, right? So we have variation when it comes to scale, when it comes to rotation, anything that you can imagine to make this as organic as possible, right? So yeah, this is basically me fiddling with the settings, density, whatever, right? Clustering. These are all the options that we decided that it would be nice to have. It doesn't mean that we always use them. Like most of the time, we keep it quite simple. We just add some kind of randomization in terms of scale and orientation and age for the vegetation, and that's it. But we have plenty of controls here if you want to make it a little bit more complicated. And something that is cool is that you can keep it simple. Like you can have just one scattering system for the entire environment, or you can have multiple scattering systems, right? So because when you're scattering, there is always an element of randomization. So what we wanted to do here is like, well, maybe I want to be a little bit more flexible, and I want to be able to scatter only one species of vegetation or one family or whatever. So we can control that independently. Unity doesn't care. You can feed Unity with point clouds that come from one scatter system or 20. Actually, we use that quite a lot. And we end up with this, just a point cloud, right? And I believe this is, it will tell us now. I think this is 1.6 million or something. And Houdini can handle that geometry, right? But in Unity, we can actually render that in real time. So that's pretty cool. So we end up exporting only attributes, and each of those points back in Unity knows what prefab should be used in there. So here you can check the point clouds. Here we can check which prefab is being used for each of those points, and dots will handle everything else, right? And you can pick and choose. You can, change prefabs if you wanted to. Here you can see the LOD system. So, it's debugging options, basically. You can see that it's been affected by the wind. We can stop the wind, make it faster, work with direction, speed, the usual parameters that you would expect. And yeah, it works very, very well. And again, we have millions in here. And a very cool thing, like we have these ground simulations. We can scatter on those as well. And the information in the point clouds will respect the movement of the ground simulations as well. We have debugging options for wind, so it's easier to manipulate. Because when you have millions, it's a little bit tricky to set the wind. So we have debugging options. And we also have a collision system that interacts with dot entities as well, right? So the characters can push the vegetation around. This is a little bit extreme, but I think it illustrates my point. All right. And here you have like a top view of this environment. It's a bit choppy in the projector, right, or the screen, but hopefully you can see it. And the loading works very well. So, that's how we manage to set dress these environments, basically. Okay, that's pretty much it when it comes to environment work. What about visual effects? We have quite a lot of visual effects, especially in the worldscape scene. So let's take a look at that. So this is basically what we have. We have ground simulations, which are basically RVD simulations and virtual animated textures. We have explosions using the 6-way lighting. We have debris and footprints that we created using the visual effect graph. We have ambers, also using the visual effects graph. We have a lot of fog using both local and global volumes. And we have also fire crafted with the visual effects graph and flipbooks. So let's take a quick look here. So this is the worldscape scene. I believe we have 21 explosions in this scene. Again, this is all 6-way lighting, which is not fully volumetric, but it does the job most of the times because it can be reshade, it can be manipulated in one way. You can interact with lighting as well. So, this was good enough for us, especially because having 21 explosions, we couldn't go other way, really. So, yeah, that's basically how it looks. At some point, I'm going to open one of these explosions. Maybe I should move forward a little bit. But you can see it's made of multiple components. So right in the core, we have these debris showers. It's basically like soil and dirt and pebbles going off. Which we barely see, but we like to have it anyway. Then we have the smoke component, which is kind of the main component of the explosion, which is actually divided in subcomponents. And I will talk about that in just a minute. And then we also have like a point light for each of the explosions, so we can control the blast, basically, right? And as you can see, we can get a little bit of interactive lighting and reshading, right? And the good thing here is that, and by the way, we also have these projectiles that they look a little bit subtle here, but when you see all of them in action, they are quite prominent, right? And they add quite a lot. And the good thing here is that we're reusing the same explosion all over. So, 21 explosions, but it is the same one. And the cool thing is that we exported the smoke elements in multiple elements, so we can modify them for each explosion in terms of timing, but also in terms of how they look. We can make them bigger or smaller. We can change the colors, the temperature. We can reshade them. So, it's quite flexible. Like with just one single explosions, we managed to do the whole thing, right? And as you probably know, 6-way lighting, I believe it's available for Houdini and Blender, so you can export all of that to Unity. These are some of the flipbooks that we are using for each of the smoke components. They don't need to be super high res or anything. They kind of work okay. Right? So this is basically how we made all the explosions. I mean, nothing that you probably don't know already. Right. We also have some other secondary visual effects that they are not as prominent as explosions, but they are important for the storytelling, like bullet hits and some other secondary visual effects. We made all of those with a visual effects graph, right? Projectiles, smoke, that kind of thing. Yeah, it's all visual effects graph. We have fire in the background. We don't really see the fire that much. We just hint that it is there. So we didn't care too much about it, but again, it's a visual effects graph and flipbooks as well. And then we have these ambers flying in there, which are pretty cool. And Rob, who made them, he's quite proud of them because they are not just particles. They actually look good from any point of view. And this is all VFX graph and I believe quite complex mathematics behind it. But they look very nice. Some RBD simulations, they are actually very low res. But once we put some scattering on top, once we texture it a little bit, and once we add secondary VFX like debris and dirt and soil, they kind of work. By the way, this is also work in progress. It's a little bit better in the final. That extra debris is also created with the visual effects graph. These are mostly particle systems. We use a little bit of geometry particles as well, but not that much because they are obviously very expensive. But you can see they are very dense, but they add a lot. And we just created multiple subcomponents so we can just play with them and puzzle them together. Same approach exactly used for creating footprints. And when the character falls, things get moved around. And yeah, we don't see much of it in the film, but everything adds to the final picture. And finally, there is this huge debris shower inside of the trench that is basically the same approach, but just way too many particles. And there was a bunch of geometry particles as well in here. Okay, what about lighting? So for lighting, we relied mostly or exclusively, I would say, on adaptive probe volumes, right? So when it comes to secondary lighting, you have multiple options with a high-definition render pipeline. Ideally, you would use, full-time ray tracing or path tracing, but I guess you wouldn't make it as performant as we did. So obviously, that was off the books. So we ended up using adaptive probe volumes. The good thing about adaptive probe volumes is that the setup is automatic. You don't really need to do much. You just click a button and Unity will do everything for you. It's per pixel lighting, meaning that the lighting consistency would be ideally better. It has streaming capabilities, which is great for performance. Obviously, you don't need light maps. You don't need extra UV sets. You don't need to create textures for lighting information, which is good when you have hundreds of assets. And, if the automatic setup doesn't work for whatever reason, you can always fine-tune things. I don't think we ever had to do it, but you have tools to do it. And we also use light blending, which is very useful because you can bake different lighting setups in the same scene. And then at runtime, you can choose which one you want to use, or you can even combine multiple light scenes. And what is good about light blending is that they share data, right? So the subdivision of the scene for streaming, the placement of the probes and all of that, you're not duplicating that data. It's being used for the multiple lighting setups. So here you can see it in action. So if I zoom out to see the entire environment or the vast majority of it, if we enable the debugging options, these are the cells that are being used for streaming. Right? If we display the bricks, this is basically the subdivision of the scene. So, it would be more subdivided where it's needed. It's a little bit more sparse outside, and it's a little bit more dense inside. And if we display the probes, same thing, right? A lot of resolution where it needs to be high quality lighting, and less resolution where we don't need that much detail. We can take a look at this environment. This is much bigger than the previous one. So you would expect more subdivisions, so streaming is a little bit more efficient. So that's what you are seeing here. The subdivision of the scene, as you can see, it's very sparse, but it's very detailed where it needs to be, which is where the action is happening. And obviously the same thing with actual props. Okay, and one last example of this. This is the trench, which is a very tight space. So obviously you need a lot of resolution inside of it because it's mostly secondary lighting. So you would get a lot of subdivisions there. But once you are outside of the trench, it's a flat, dull environment, so you don't need as many props. Right? Okay, so now Chris is going to talk about how we build the character for Time Ghost.
Thank you. All right, so I thought I'll cover some of the work we did on the character for the Time Ghost cinematic. And first of all, in the early days, we actually started to build one of the outfits actually sewn up by a tailor. And then we used that to scan some of the pieces for the clothing and use that as a reference to actually hand sculpt and model some parts for the character. This was on a very early concept for the character, but yeah, we used that. Right, so to make the character move, you need a rig. And in this instance, we used Autodesk Maya to complete all the animations. A rigging framework called MGear, which is open source, that kind of helped us kick it off quite fast, and also make all these additional rigs for the belt straps, the gear, etc. The animation data we got from regular optical mocap data that we shot. We also used Extensuit to shoot some of the running sequences on the fields. And of course, regular keyframe animation on top of that. Right, so the character have 3 layers. Basically, it's the outfit, which is the whole full dress. Then we have the coat, and oh, it doesn't loop here. Just play. And then on top of that, we have all the gear. So for the coat, we wanted to have a little bit of a specific look and feel to how it deformed. So for these ones, we ended up doing offline simulation in Marvelous Designer. Then we actually took that back into, or converted that with DEM bones to a regular skinned joint-driven mesh, which we then dropped into Unity and played it back as a regular animation. So we did that for all the shots where the coat was needed to deform. The second piece here then is the outfit itself. And we wanted to add a little bit more detail to how this one deformed. So we started to look at machine learning, how can we actually make all the wrinkles, etc., behave the way we wanted them. And we made a custom model in TensorFlow, and with the Sentis framework in Unity, it makes it really simple to add this. And with a lot of help from the Sentis guys and Alexander Ribard, we actually, at the shipping time, had it running at 0.72 millisecond on a 360 card. I think I measured that one. And the scheduling was done at 0.32 millisecond. And this is actually deforming 115K vertices in runtime, and that's 228K tries. So the video here, you can see the regular skinned object and what the deformer adds on top of that. I'll break it down a little bit more, how the process worked. But one thing when you actually start to R&D this stuff is, I just wanted to highlight that the Sentis framework allows you to drag and drop ONNX models directly, and that really helps when you start to sort of explore these venues. You train the model, you can use a DCC tool like Autodesk Maya or Blender, and export the data, train the model, play it back in your DCC, and the exact same model you can drag and drop into Unity and look at the result there as well. So that made it super nice and easy to explore this kind of option. And this is a nice deformed pants in the early days. Right, so for the, I'll just loop these ones. Let me play. There we go. So for the full outfit then, we grabbed about 70 poses, and that's from the cinematic, what the characters were actually doing. And some of these poses were hand sculpted with the rig. So basically it's going from neutral pose to the end pose. And we brought these ones over and made an offline simulation in Marvelous Designer. So if you look up here to the right video on the far left, you can see the output of the mesh cache from Marvelous. The middle character there is the skinned one, and at the far right you have the delta data between the skinned one and the deformed one from Marvelous Designer. So with that delta data extracted, we bring that into Unity, where we actually do the final extraction process, to say, where we take 17 joint rotation or quaternion values, and then we play back the delta vertex values as well at the same time. So that gets fed into the model and train it, and it takes about an hour to do it. And then you drag and drop that model and look at the results. Another instance where we kind of looked at using machine learning was for all the background characters. We have about 85 to 90 of these running, not all in frame at all time, but maybe 10, 15 popping in and popping out. And for this one, it wouldn't have been feasible to do a simulation for each and every one of them because they tended to update quite often, and we moved them around and fixed the animations. So we took a small portion of the run sequences, made a simulation of that lower part of the code, and converted that one to dem bones as well. And that we sort of fed into a tiny model, which is about 500 kilobyte in size, I think. And the nice thing then is we can use that one model and actually run back inference on at runtime. So whatever character was on screen, we sort of throw that on the model, apply the deformation, and all of a sudden, all the characters have deformation on the lower coat. So that's about 49 joint targets and 4 driver joints for the background characters. So another thing is the hair system that we updated or throw a lot of work into. We added a wind system, automatic loading, and accurate collisions for this. can show. There's one shot here in the sequence when the character actually pulls off the helmet, and that is no kind of flipping on and off the hair. It's actually being pushed down by the helmet, so it all interacts with the outfit. And the other video, you can see the loading here. It's being controlled manually to show, but it really boosts the performance because the viewing distance from the camera or the view space, you maintain the overall shape and volume of the hair and the shading, but you're decreasing the amount of computational power to actually simulate the hair. So this is super nice. We can see some more shots here from the engine. Is when he pulls the hand through the hair, and you can see the really nice interaction between the fingers and the hairdo, that there is no collision there. And we're running at 12 sub-steps per frame, so that's 360 physics updates per frame to achieve this. And if we scrub through here a little bit forward, you can see the kind of wind system. And since everything is interactive, you can start to pull around all these sliders to get a different result or the look and feel you want. And it's actually super fun to sit and play with. Same thing a little bit down here. If you want a different hairstyle on the fly, you can start to play around with these sliders. And the results sometimes can be quite fun to watch, but it all works. So you could play this animation back and it will still interact with the colliders on the hand. And another thing I wanted to highlight was the thing we call the fuzz. We have this on the character throughout the cinematic, which is basically about 40,000 tiny hair strands sticking out from the outfit. And we also have the peach fuzz for the hair, the face. Oh, I should loop that as well. Sorry. So it's using the same hair system, but it's not dynamic per se. It's just pretty much static strands that we attach. But it all plays along nice and follows the character and the deformation of the formed outfit and the skinned mesh. And it really helps to break out the silhouette and add tiny specular highlights to the mesh, etc. So that's also a super nice feature. And yeah, a few things during production. Things doesn't always work out, and you go a bit mad sometime, but afterwards it's quite funny to watch. But at the time you go, what just happened? So these are some of the highlights. There are plenty more. Right, that's about it. Brief overview, and if you guys have any questions.